Good morning. Today we're going to first of all discuss what happens with the electric and the magnetic field when we introduce retardation effects. Then afterwards we're going to see if we can figure out the fields and the potentials from a moving point charge, the so-called Liénard-Wiechert potentials. Now, we said before that we can't simply evaluate the expressions for the E field given from the charge distribution at the retarded time. That doesn't give us the full physics. So we're going to discuss that as well. But first of all, we're going to show that the form of the potentials which we introduced more or less like a mathematical trick, which was that E is equal to minus gradient of V minus time derivative of A. And similarly for the B field, curl of A. We will show that this does in fact follow very naturally from Maxwell equations. From the Maxwell equations, and we will do that by using the power of the Green's function, which we discussed this Monday. We start out by looking at the Maxwell equations in a vacuum, but this time with charges and currents. Gauss law. Let's see. Since we're in a vacuum, I'll jump right to the electric field and the magnetic flux density. Faraday's law. Finally, the Ampere's law. Like this. And now we're going to derive the wave equation for the E field and the B field, this time keeping the sources, because now we're interested in where the electric and the magnetic fields come from. I mean, starting from the sources, where does the electromagnetic wave, for example, come from? So first of all, to find the wave equation for the electric field, I take the curl of this equation, the Faraday's law, and we get that the curl of E is equal to, from exercise 1, the gradient of the divergence of E. This I can write as rho over epsilon naught, of course. And just to stress the point, we're interested in the general case where we have both space and time dependence of the sources. So the current as well is dependent on space and time. But I'll drop that because it saves me a lot of writing. But just remember that we're in the general case now where everything is time and space dependent. Also we had the Laplacian of E. And this becomes the gradient of the charge distribution, as well as the Laplacian of E, right? Now that was the left-hand side of the Faraday's law. The right-hand side is this one. So if I exchange the order of the time derivative and the curl, I get minus dt curl of B, which I can write as, I can write the curl of E like this. Let's see, equals minus mu naught, the time derivative of the current, that's this term, as well as the second time derivative of the E field. So this is the left-hand side, and this is the right-hand side of my equation. Now if I gather the terms with the electric field on one side and gather the source terms on the other side, we will find that the wave operator on E is not equal to 0 anymore because we include the sources. So we have one term which is the gradient of rho, and one term which is the time derivative of the current. Like this. And this is the wave equation for the electric field. Now if you, let's see, should be a plus sign here. Now if you recall from last time, we found the Green's function for the wave operator with the boundary condition that there's no field at infinity and some source on the right hand side. And that's exactly this equation. So we used a lot of time to find the Green's function for the wave equation, and now we can reuse it again. This is exactly the point of the Green's function, that you can use it again with different sources. And but the equation is mathematically on the same form as for the potentials. So this is a wave equation with source terms, and we know the Green's function for that. So I'll write it down. R t r prime t prime is equal to minus the delta function, which gave us the retarded time, t r minus t prime, divided by r minus r prime. And there was a 4 pi as well. Okay, and just recall that tr is the retarded time, and we can write that as t minus r prime divided by the speed of light c. Okay, and the solution of this equation then, well, I can write that down because when I know the Green's function, I know the solution. And it is simply the following. So the electric field as a function of space and time is equal to an integral over the Green's function and the sources. So I integrate over the prime coordinate system, g of r t r prime t prime, and the source term, that's these two terms. Let's see. So I have the gradient of the prime coordinate system, and now I'll be careful because we have both unprimed and primed coordinate systems, and the time primed over epsilon naught, that's just a constant, plus the current term, which is simply the time derivative, again with respect to the primed coordinate system, because it's inside. I integrate over the right hand side, so I introduce the primed coordinate systems to separate the observation point from the integration variable, as we always do. Let's see. Yeah, and the current at r prime t prime. Okay, so this bracket belongs to this one. Right, now I can, what I'm going to do now is to start out from this integral, and I'm going to perform a partial integration to get this gradient here in front of the Green's function here. Now I will assume, as we ordinarily do, that the charge distribution is localized. It doesn't stretch off to infinity. It's just some localized lump over charges or currents. So if I go far away, then it's going to look small and so on. It's not, for example, an infinite plane or anything like that. So a localized charge distribution means that the surface term is going to go to 0 because rho and j go to 0. Okay. Okay, so we start off by examining this integral and trying to perform a partial integration. And then, if I do that, I get that the integral over d3 r prime dt prime g of r t r prime t prime, the gradient prime of rho of r prime t prime over epsilon naught. That's my integral to solve, is equal to the following. First of all, there's a surface term, which is the time. Yeah, I'm performing the spatial integration now, right? So I get, take the integral of everything inside with respect to space, and the time integration is still left. So when you perform the partial integration, you get this factor without the derivative, right? So you get g with all that stuff times rho over epsilon naught at r goes to infinity, right? So that's the boundary term, the surface term, if you want. And then I get the term where you have the nabla moved in front of the Green's function, which looks like d3 r prime dt prime, put a bracket, and now a nabla prime with respect to the Green's function. And finally, the charge distribution without the gradient in front anymore, rho of r prime t prime over epsilon naught. And now the Green's function has a lot of symmetry in it. For example, if I exchange r with r prime, then the Green's function is unchanged. This is a general result, but it's for our special case, it's very easy to see that that's the case. However, the derivative changes sign if I change r to r prime, meaning that minus the gradient with respect to the unprimed coordinate system of the Green's function is the same as the gradient of the Green's function with respect to the primed coordinate system. This follows from the defining equation of the Green's function. But I'm not going to spend time on proving that. But that's a general, that's a property of the Green's function because of the spherical symmetry here, right? The Green's function depends only on the distance from the on the distance between t and t prime, like here, and also r minus r prime. Okay, and this means that because the integral is with respect to r prime, and this is with respect to r, meaning that I can take the nabla and move it outside the integral. So a lot of fuss about moving a nabla a little bit around. So we get that this integral, if I continue here perhaps, this big integral, well, this term vanishes, and this integral, take the nabla outside, so I get minus nabla integral of d3 r prime dt prime g of everything, rho of time and space over epsilon naught. Now if you look at the Green's function, the time dependence is really easy. It's just a delta function. Here? Yep. Right. That's what my notes say as well. Okay. So we found that the Green's function was simply a delta function in time. So I can perform the t prime integral without knowing anything about the charge distribution. Meaning that we get out minus the gradient d3 r prime. I simply insert the Green's function And the delta function gives me out rho of r prime tr, the retarded time, over 4 pi epsilon naught r. And as always, r is equal to this distance, r minus r prime, like this. Okay, and I can do the same trick, exactly the same trick, in the second integral. So I kind of simplified the expression for the first integral. Now I'm going to do the same thing with the second integral, which is over the current density this time, except now I'm going to do the same thing with respect to the time. Okay. So performing exactly the same trick, I will get the time derivative outside the integral because of the properties of the Green's function. So using that dt prime of g of all the 4 variables is equal to minus dt unprimed of g of all the 4 variables, I get that the integral over d3r prime dt prime, and I skip the constant. No, wait, there's room for it here. Mu naught, and there's dt prime j, the current density of r prime t prime. Same trick, get this, no, wait, there's a Green's function. I move the time derivative in front of the Green's function by the partial integration. I swap t for t prime using this identity here. And I get out simply that this integral is equal to minus dt integral of d3r prime j of r prime and the retarded time over r, same r as before, and times a numerical constant, which isn't all that interesting by itself. Now I'll wipe the board and then we'll collect the terms and see what we got for the electric field. Okay, so collecting the two integral terms, I get that the electric field is given as, first of all, the gradient of one integral, which was over the charge distribution, is d3 r prime, charge distribution at the retarded time, as we would expect, over 4 pi epsilon naught r minus the time derivative of the other integral, which was over the current density. So that's d3 r prime mu naught over 4 pi j of r prime and the retarded time, as we'd expect, over r. Okay, and if you stare at this, well, then you'll realize that this first integral, that's simply the potential. And the second integral is the vector potential. Meaning that starting from the Maxwell equations, deriving the wave equation, and then doing some tricks with the famous Green's function, I get out that the electric field is simply given as the gradient of a potential minus the time derivative of a vector potential. So this was, the Maxwell equations really encouraged this from the beginning. Any questions? Okay, the derivation was clear? Right. Now, if I do the same thing for the B field, I guess this won't be very surprising now that we did this for the electric field. But, well, when we take the curl of Ampere's law, we get that the wave operator on B is equal to minus mu naught the curl of J. Okay, so again, it's the wave equation with a source term, and we know the Green's function for this equation, meaning that I can simply write down the solution, and it looks like the following. The integral over space and time, and the Green's function. I skip the time and space dependencies, cross minus mu naught the curl of J with respect to the prime coordinate system like this, the Green's function and the source term as always. And if I do the same trick, I can first by partial integration get the curl in front of the Green's function and then exchange the unprimed with the primed coordinate system. Then I can take the curl outside and I obtain the following, that the curl with respect to the unprimed coordinate system is d3 r prime mu naught or 4 pi r j of r prime at the retarded time. That's simply the curl of A, right? Looks exactly like the integral over the charge distribution, except now we have the current, so it's 3 components. Otherwise, it's the same. And we show that in the same fashion as we show that the electric field was given from these 2 potentials, the B field is given from this one potential, the vector potential, in this form. So it's we see that the potential formulation follows quite naturally from the Maxwell equations for both the electric and the magnetic field. Yep. No, I think that's a typo. So this is simple multiplication, because the Green's function is, of course, a scalar. If you recall the definition, then linear operator on the Green's function is a delta function, right? And the delta function is not a vector. So, wait. Well, the Green's function is a vector if the unknown is vector valued, isn't it? Because then, let's see. Well, I have to think a bit. Well, now it should be simple multiplication. You should think of it component-wise, I guess, to be safe. But yeah, it should be simple multiplication there. Must be. Yep. Anyway, I think you get the point from the derivation that the potential formulation follows clearly from the Maxwell equations. So I think I'll get back to this if I'm wrong. Okay. Yeah. So we're convinced that the potential formulation is a good idea, I hope. Okay. Now, next topic is when we find the potentials, then how does the fields change when we have retardation effects? And this is the most straightforward way to examine this issue is to first find the solution for the potentials, which we've done now, and then find the fields by taking the derivatives of the potentials, which is it's usually easier to go that way, because if you want to find the potentials from the fields, then you have to integrate, which is hard in general. And now we'll try to figure out how do the fields change when we have retardation effects, because we realize that we can't simply insert the retarded time as we did for the potentials and be happy with that. So let's start off by writing down the standard expressions for the potentials. And they were the following, that the potential is given by an integral of the charge distribution at the retarded time, like this. And similarly, the vector potential is given by, let's see, mu naught over 4 pi, and then an integral in the same form. No, wait, that's a bit too similar. Also here at the retarded time. Okay, and just to recap, TR is equal to T minus R over C. So TR is a function of the distance between the observation point R and the integration point R prime and the time T. And yeah, R is R minus R prime. Okay. And if we now look at the expressions for the electric and the magnetic field, which are the following: E is the gradient of a scalar field or a scalar potential minus the time derivative of a vector potential, and the magnetic field is the curl of a vector potential. Now, if you look at this, in the electrostatic case, we had simply this term. And then I can just take the gradient here, and I get one term for the electric field as well. But now realize that the time here actually depends on space as well, meaning that this spatial derivative is going to give me an extra term from the chain rule here. And in addition, from the electrostatic case, I have this, when I go to the electrodynamic, more general case, I get this term with a time derivative of a vector potential, which is also going to give me a new contribution. So, and the B field, well, there's no new term when you go to electrodynamics as compared to magnetostatics, but the spatial derivatives in the curl is going to add an extra term because of the space dependence on the retarded time. So I'm going to try to use the known expressions for the potentials here, as well as the standard way of calculating the electric and the magnetic field from the potentials, to get a new expression for the electric and magnetic field and try to compare with the static case. So I will need the gradient of this integral, and I will need the time derivative of this integral to get the electric field. So I start off by looking at the gradient of this first integral. So gradient of V is the same as the, let's see, 1 over 4 pi epsilon naught d3r prime. I move the gradient inside the integral because it's with respect to a different coordinate system. So the gradient of rho of r prime t r over r. And now the dependence on r vector without the prime is in the retarded time and in this denominator, meaning I can actually perform some operations to see what this means without knowing the spatial distribution of the charge distribution itself. So if we recall then this and this and use the chain rule, I will look at the ith component of this gradient. So what I'm interested in is di of rho of r prime, which is of no significance with respect to this derivative, and tr, which does contain r vector over r. And if I do that, I first get a contribution from the numerator. So I get rho over dot r prime tr. So first I take the derivative of this with respect to tr, that's a dot, and I multiply by the chain rule term, which is the di of tr, which is simply di of r, right? So that means I get out minus 1 over c di r, a bit close. Okay, divided by r. That's the first term when I use the product rule on this times this. And the second term is minus rho of r dr over r squared times the chain rule term from this one. That's di of r. So next order of business is to figure out what is di of r. Note also that here I put the over dot because d dt, or perhaps I should say partial derivative of time, is equal to the partial derivative of the retarded time, because the retarded time is simply the ordinary time minus something that does not depend on time. So so those derivatives are in fact the same. So this over dot simply means the time derivative of this function, as is a common notation. Okay. Now if I write out r in a special form, this will be a bit easier to calculate di of r. And I write it as r minus r prime, which I can write as xm minus xm prime times the same thing this is a dot product with itself, right? I take the square root to get back to the length. So what I need to do now is to calculate di of the square root. Let's see. So that means that di of r, when I write it on this form, will be simply 2 times xm minus xm prime divided by r, 2r. The factors of 2 cancel, and dixm. I'm differentiating with respect to the unprimed coordinate system, right? But this is, of course, the Kronecker delta, because if I take the derivative with respect to x of y, well, then I get nothing. Otherwise, I get 1 if they are the same. So this is delta im. Okay, and that simply gives me xi minus xi prime over r, or ri, the ith component of the vector r over the length of vector r. Whew. So if I get all this back into my differentiated integral here, I get that, let's see, minus grad v is equal to 1 over 4 pi epsilon naught d3 r prime. I get one term that's on this form, and this other term here. First, well, that follows from the product rule, right? And the derivation we did here. And it looks like the following: rho of r prime t r over r square. So that's this term here, plus rho dot, again this is the time derivative, r prime t r over r times c, end of the bracket, and finally an r hat, because this now is essentially an r hat, right? So if each component looks like the component of r over r, well then that simply means that the gradient of r is r hat. So that's this common factor here. Yeah. So because of this this property here, that the derivative with respect to time is the same as the derivative with respect to retarded time, the second term in calculating E, the time derivative of the vector potential, does not change. Meaning that I now figured out everything there is to figure out about the electric field, and I can write down the final answer. So, final answer. The electric field can be given as a set of integrals over the charge distribution and current distribution. First term is the same as in the electrostatic case, rho of r prime t r over r square r hat. Second term had a time derivative of the charge distribution, over r hat. And finally the vector potential term was the same as in same as before we started working with retardation. Now evaluated at the retarded time. Let's see. So if I put a bracket here and here, that should be it. Now notice that this term here, that's the electrostatic case evaluated at retarded time. So if we naively insert the retarded time into the electrostatic expression, this is the only term we would be left with, right? But because of the the space coordinates started depending on time because of the retardation effect, we added this term, and because we added the time derivative of the vector potential, we added this term. So these are extra terms with respect to the electrostatic case. And in particular, this term is not naively expected. If, say, you introduced the retarded time but included this term, you still wouldn't get this one. And this equation here is called the Jefimenko's equation. For the electric field. And this equation is not necessarily very convenient because these integrals are frequently not trivial. It's often easier to explicitly calculate the potential first by solving this integral and then inserting into these expressions here. But I think it's kind of satisfying to generalize the expression we found from the electrostatic case to the more general electrodynamic case with retardation effects. So that's why we include this. And to see that you can't simply evaluate everything at the retarded time. You have to start out from the theory and work your way up and figure out what does in fact change. And it's not trivial to see from before you actually start doing the math to see where you get some extra effects. So now let's do the same thing for the magnetic field. After Skal vi se. Hva med den? Sorry. There's a time derivative on this J, of course, because this is the only place where you have a time dependence in the vector potential. So yeah. So this dot is added from the time derivative. Yeah. And I think we continue after the break with the B field.